all of the time from some number p. Of course, it depends how fast your network is. So if you have a really fast network, it may be still helpful, even for large number of p, for large p, but still. So this is one deblocking. This is the simplest case of what people typically do. But there is a better way, and I think it's even an optimal way. Okay, let's try like this. This is also again the example that the same problem can be solved by different algorithms, and there are bad algorithms and worse algorithms. So this is a better algorithm, which is better in terms of reducing the communication cost. So the algorithms can be bad in terms of accuracy, they can be stable or unstable, they can be well fast and slow, but if you go from a laptop to, they can be also good or bad in terms of utilizing the cache. And here, the algorithms are either good or bad in terms of communications. And for different computational platforms, one algorithm can be better for one platform, and another, but it may be worse for another platform. So again, if you try such kind of algorithms to implement over, for example, Hadoop type of architectures, you really need to develop absolutely different type of algorithms rather than even those algorithms. So you really may have to increase the number of operations. So one of the examples is how you compute QR decompositions on Hadoop architecture. So 2D blocking. So it means basically that you split your matrix into blocks, and then each processor, so that now the processors, they are numbered not by single number but two numbers, and each block of the matrix is stored by each process holds a block, not the whole row but only block, and a part of the vector. So then if you need to multiply, I will go to the details, but then, so basically you need to look, if you multiply the column by row, you multiply the local one, and then you do communication. Okay. And then you basically need to sum up. Then you need to sum up the small vectors computed for each, on each processor, and at this point you do this communication. Okay. So that's just the summary of the so see, if you have P processor, now the block size that you can afford is square root of P, right? So each machine has the block of size n over square root of P times n times the square root of P, and the vector of, again, length of n over square root of P. The number of operations you make at each block is still n square over P, it's the same. So this splitting, of course, doesn't reduce the number of operations that is done. However, if you count the number of sending and writing data, it's completely different. You have again the same term for that scales logarithmically with P, but number of writes is now actually decreasing with the number of processors. It's n divided by square root of P. Okay, it's multiplied by log P, but this is function that when you increase P, this part decreases. So if you have, well, formally speaking, if you do like this, then and you increase P, then the communication cost will also decrease for a wide range of number of processors. Okay? So again, this 2D blocking helps to decrease communication cost. So for 1D blocking, there was just n here. And for 2D blocking, you have n over square root of P. Any questions? Programming these things is much more complicated, well, compared, I don't know, to writing Jupyter notebook. For example, you have a large machine, you have to submit jobs in a batch form, so basically write scripts and submit the scripts. Usually the machines come with skilled administrators that are able to do that, but not always. And there are some implementations for this distributed linear algebra. Well, the old one is Scala-Pack, Linus has a lot of support. So if you manage to write it down correctly, manage to install the corresponding dependencies on a cluster, then it may not be so difficult. So in Python there is a wrapper, okay, for Py. At least it can be used for testing on multi-core machines. So of course, well, MPI is mostly suited for distributed computations when you do not have shared memory. So you have many nodes connected by a network, and the MPI daemons are running over that, but in principle you can run the code just on a multi-core machine with a shared memory. It will still work quite well, at least for testing is okay. So installing this is quite easy. Installing this on a cluster, well, it's not so easy, but it's possible and people do that. Running Python on tens of thousands of cores, it's not an easy task. So there are many funny things. What may happen if you run I think it was several years ago, and there were funny problems about running 32, I think, thousands of processors on the Python. Okay, not going into details because I don't remember them 100% correctly. For large-scale deep learning, we need a lot of GPUs, and well, you can have several GPUs on shared memory, but if you really need a large-scale setup, okay, even training ImageNet from scratch is not an easy task. So I think that now the record, how much it was, 1,000 GPUs, something like that, was 224. This is a cluster. So there are no machines with more than maybe 10 of cards on shared memory. So if really large-scale computations are needed, well, ImageNet is one, well, more or less academic example, but training networks on ImageNet is not fast. And if you go from, and the images are not big, so only 224 pixel, right? And if you go from two-dimensional images, for example, to videos, then training a reasonable neural network without a really large-scale GPU will be just a sort of nightmare. And that's the set of technologies that you need to use. And well, we have in the cluster with about 100 GPUs, which is not this V100. That's the one that I mentioned. But again, you need to basically install the software, tune the software, and run even the algorithm. So PyTorch has this. It has different backends. I think it's MPI and something else. There are also programming languages which we don't talk about. One is Julia, which specifically one of the features is really easy parallel computing. Sort of, and okay, one of the dreams of numerical analysts was development of automatic parallelization tools, so that you don't have to do anything. You just get the code, boom, boom, and you get automatic parallelization. It never works, and probably it will never work. But still, you may have computing primitives developed in these libraries that already implement basic operations like scatter the matrix, do distributed matrix factorization, and so on. Yeah, so PyTorch has support. Well, I would not say 100% mature, but it seems to work. But working with this kind of, it's not so simple like working in a standard setup. So that's the summary of this part. So basically, that's one way. If you have a large matrix and you need to do something with it, like multiply or factorize or solve linear system, one case is just do not do any development of fast methods, just take a larger machine with many cores if you have an access to it, right? So still having an access to such kind of machine is not always the case, but it might work. So then you distribute it, probably use some library for that, some of the packages. especially for sparse matrices and different communication scenarios, developing these parallelization schemes, blocking and so on, is not as the problem that is 100% solved, and people still develop better algorithms for that. But this is sort of brute force approach. We don't have enough memory, just add more memory in terms of distributed computations, and that's what people were doing always. And if you have large, sometimes even storing a single vector may be a big problem. Even if you have a sparse matrix, storing a single vector is a big problem. Or maybe you come to the point that you need fast computations. One example, when you really need fast computations, I like a lot, is, for example, weather prediction. So if you do weather prediction for 1 day, and your computation takes 2 days, that's a bad idea, right? So, and all large-scale weather prediction projects, well, for short-term weather forecasts, they use high-performance machines for that. So if you do like climate prediction on a long term, you can wait, but for short-term weather prediction, which is actually, well, people often blame, but it's actually improved, tremendously improved. Even in Russia as well, the quality is now much better. Okay. So, that was the summary of the part. So sometimes you may need high performance computing. So if your problem is large, but then typically you run out of memory. Sometimes some problems need real-time computations, but yeah. Another way is to use structure, and one of the most important structures is the class of sparse matrices. Right? So the sparse matrices, well, I will try to give a formal definition. The matrix is sparse, that it has so many zeros we can make use of. Right? So if it only has one non-zero element, probably that we cannot use this fact. But if it has almost all, right, maybe, well, but then it depends. So if you have a million times million matrix, it only has 1% of non-zeros, but whether it's good or not. 1%, so the total number of non-zeros is n squared is 10 to the power 12, right? And 1% is 10 to the power 10 non-zeros. If you divide it by the size of the matrix, 10 to the power 6, you get something like 10,000 non-zeros per row. And actually this is not a sparse matrix. So measuring sparsity in terms of percent of non-zeros is a bad idea. A much better idea is to measure the sparsity by the average number of non-zeros per each row of the matrix. So if it has, for example, 50 non-zeros per row on average, 100 non-zeros per row, and the size of the matrix is 1 million, this is okay. This is a typical sparse matrix. And the number of non-zeros per row, per column, it plays the role of the number of neighbors. How many neighbors each element has. So we have such sparse matrix. We will discuss today basically how we actually store the matrix and basic stuff about how we solve linear systems. Yeah, what we want to do, we want to do the same things that we discussed for dense matrices. So we want to solve two basic problems. We want to solve linear systems, and we want to compute eigenvalues and maybe singularities. So two basic problems. So in the dense case, we use matrix factorization, we use ALU here, and we use short decomposition here. So unfortunately, short decomposition for computing eigenvalues is not possible for large sparse matrix because both the orthogonal matrix and the triangle matrix, even in the symmetric case, the orthogonal matrix will be always dense. So if you have large sparse matrix, I do not know of any case where you're able to compute all the eigenvalues. So solving the full eigen problem for the large sparse matrix is sort of not possible because, well, you can store the vectors. Well, at least I have not heard about such examples. So the only thing is that if transform this matrix onto large clusters and try to compute them. But solving partial eigenproblems, so computing only largest eigenvalues, smallest eigenvalues, so eigenvalues in a particular range, this is possible, and that's what's typically meant when people speak about eigenvalue problems for large sparse matrices. They compute only part of the spectrum, which is related to certain vibrational frequencies and so on, for example. For solving linear systems, you can compute analog of Gaussian elimination, but there are a lot of difficulties which make this different. I will discuss it. But typically, what is used both for solving linear systems and for solving partial eigenproblems, these are iterative methods which utilize the matrix by vector product. So you have the matrix and you multiply this matrix by vector. And that's the main atomic operation. You have a sparse matrix, we need to multiply it by vector.